We already mentioned all these different kind of automatas and grammars: finite automata, push down automata, linear bounded automata, Turing machine. So these are automata, and regular grammar, context free grammar, context sensitive grammar, context sensitive grammar, and unrestricted grammar. So these are all grammars. Now all of these are model of computation, and for these models we have this deterministic version and non-deterministic version. Here also deterministic and non-deterministic. For Turing machine also deterministic, non-deterministic. So we have so many models, so many mathematical models to capture some kind of computer. Now in our entire course we will see that some of these models are equivalent to each other, and in a couple of slides we will explain what we mean by equivalent. So this deterministic finite automata is equivalent to non-deterministic finite automata, equivalent to regular expression, equivalent to regular grammar. So all these models are equivalent. So similarly, this deterministic push-down automata and deterministic context-free grammar, they are equivalent. This push-down automata, the non-deterministic version. So this is equivalent to context-free grammar. So linear bounded automatas are equivalent to context-sensitive grammar, and deterministic Turing machine, non-deterministic Turing machine, they are all equivalent, and these are equivalent to unrestricted grammar. Now these models are weaker than this model. So these models are strictly more powerful than these models. Okay. Similarly, these models are strictly more powerful than the previous two classes of models. And similarly, this LBA is strictly more powerful than push down or finite automata. And finally, we have Turing machine. So Turing machine is the most powerful. So this is all powerful. Okay, this is the most powerful of all the other models. So now we will explain what we mean by equivalent and strictly more powerful. See, the job of all these models is to solve some computational problem, right? And the computational problem, we have reduced that to some language. So to solve the computational problem means to construct some model which can accept the language associated with that problem, right? And what was that language, if you remember? So that is precisely the set of all strings for which the answer to the decision problem is yes, right? So if you forgot that, then see previous slides. So now what do we mean by DFAs and NFAs are equivalent? So it means that if we can solve a problem by using a DFA, then we can also solve this problem by using an NFA, and vice versa. If we can solve it using NFA, then we can solve it using DFA. So in terms of language, how that statement will translate into that for all DFA-D, okay, for all DFA-D there exists some NFA N such that the language accepted by this D is the language accepted by this N. So that means if we can accept a language using some deterministic automata, deterministic finite automata D, then we can also construct a non-deterministic finite automata which accepts the same language. And similarly, if we can accept a language, so using say N, so for all N, for all NFA N, there exists some DFA D such that their languages are equal. So that means take any NFA N. So for that we can construct a DFA D such that this DFA will take the same accept the same language as that of the language accepted by n. So that means in terms of problem, this DFA will solve the same problem as that of the non-deterministic thing. So in this sense they are equivalent. So when we look at a language, if we say that okay, it is accepted by some DFA, it's same as saying it's accepted by some NFA and vice versa. So the set of all languages accepted by DFAs, so then this will be the set of all languages accepted by NFAs. So see, we are talking about so we are now talking about set of languages. Okay, so we started with symbols, then we constructed strings out of that, and then we said that a set of string is a language, and now we are talking about set of languages. Okay, so the set of languages accepted by DFAs will be the set of languages accepted by NFAs. If this is true, if you believe that this is true, we will prove this later. And similarly, there are other equivalent computational models like regular expression and regular grammar. So they will also accept some language, but we will show that all these things are equivalent to each other. So the set of all languages accepted by any of this type of model. So this set of languages is actually same. So now this set of languages, okay, so this is called a regular class of regular languages. Sorry, I just put it but anyway so this set of languages will be called the class of regular languages. So this class of regular languages, this is in some sense is more fundamental than thinking about DFA or NFA or regular grammar or regular expression, something like that. So all these DFAs, NFAs, regular expression, regular grammar, they are different models to solve problems in this class, right? But this class of regular languages, or if you can think of these languages as problems, so this class of problems, so this is the regular class. Okay. Now similarly there is some model called push down automata, we call it PDA, and there is some kind of grammar. So we have already seen one example of context free grammar or CFG. So it's the same thing. If you can accept a language using a PDA, then you can also accept that language using a CFG and vice versa. If you can accept a language using CFG, then there exists a PDA which accepts the same language, just like before, but here instead of DFA and NFA, you can have PD and CFG. So then again we can talk about the set of languages that is accepted by PDA or the set of languages accepted by CFG. So that set of languages, so that would be same for the CFG and PDS, right? And we call this set of languages as the class of context free languages. So now we are talking about language classes, right? So they are called the CFL, context free language classes. And again, this represents problems that these models can solve. Okay. And in terms of solving problems, they are kind of equal in power. And the same relationship holds between linear bounded automata and context sensitive grammars. Again, the set of languages accepted by LBA is equal to the set of languages accepted by context sensitive grammars, and this class of languages is called a class of context sensitive languages, CSL. And finally we have deterministic Turing machine and non-deterministic Turing machine and unrestricted grammar. Again, they are equivalent, and the class of languages corresponding to these models, this equivalent models. So this is the class of recursively enumerable languages, or we call this RE languages. Okay. So as I said before, Turing machine is the most powerful model that you can have. Okay. So this class of problems, or this class of languages, so this is the largest class of problems that you can solve using any computer at all. Okay. So there are problems which cannot be solved using any computer. So now this was about equivalence of models, and we said that that equivalence defines a class. And now what do we mean by one model is strictly more powerful than another model? For example, we said before that these PDAs are strictly more powerful than DFA or NFA. So now we know that DFA and NFA are equivalent, right? At least we stated that. So now what do we mean by that this PDAs are strictly more powerful? So it means that if a language is accepted by some DFA, then it is also accepted by some PDA, right? So in terms of problems, what does it mean? That if you can solve a problem using a DFA, then there is a PDA which can also solve this problem. But the converse is not true. So there exists a language, okay, which is accepted by a PDA, but there does not exist any DFA that can accept that language, a particular language. So that corresponds to some particular problem, okay, some particular computational problem, and that problem can be solved using this model PDA, but that problem cannot be solved using this DFA. That means it cannot be solved using NFA or regular grammar, because those are all equivalent, right? So that means that problem doesn't belong to the class of regular languages, right? And this class of CFL, if we consider, so what was that in the previous slide? I've already mentioned. So these CFLs are languages which are accepted by PDAs, right? So if we consider the set of all languages accepted by PDA, so then that will be a strict superset of the set of languages that can be accepted by DFAs, right? It comes from the first property, so this property or this property. Okay. So in that sense, the class of problems that can be solved using PDA is a strict superset of the class of problems that can be solved using finite automata. So in that sense, PDAs are more powerful, right? So we already mentioned this equivalence between these models, and we said that now this is most powerful, and so this is more powerful than this is more powerful than this. So it is a strictly more powerful. And the corresponding language classes are this. So this is the set of all languages that can be accepted by any one of these models, is a set of languages which can be accepted by any one of these models. So here we have the corresponding language classes, and here we can see that this is a strict superset of this. This is a strict superset of this. This is a strict superset of this. This is a strict superset of this, and so on, right? So we have this inclusion between this class of languages. And as I mentioned before, so this is the most powerful computer that you can have, Turing machine, right? And here the deterministic and non-deterministic models are equivalent. And we have this corresponding language class, recursively enumerable language. This this is the set of languages which can be solved using Turing machine. Now there are languages outside even this, right? Even outside it. And what does that mean? That if there is something outside this, that means that cannot be solved using Turing machine. That means that cannot be solved using any computer. Okay. So no matter what computer, even if you give it infinite space and time. So in algorithm class, perhaps you studied about time complexity, space complexity. So you know that some problems take order n square, some problems take n log n. So doesn't matter, you take n to the 100, n to the 1 million time or space. But these problems cannot be solved using any computer. So such problems do exist. So that is a very profound result. So we already mentioned this inclusions. So this class of regular languages is a subset of class of context-free languages. Class of context-free is a subset of class of context-sensitive languages, and so all these inclusions we mentioned. So put in a Venn diagram, it looks like this, right? So this regular class is a relatively smaller class which sits inside this, which sits inside this and this. And then outside all this we have this non-recursively enumerable language, okay, which cannot be solved even by this all-powerful Turing machines. Now this classification, this specific classification between regular, context-free, context-sensitive and recursively enumerable, so this is known as Chomsky hierarchy. So Chomsky initially came up with this classification depending on grammar. Okay, so the grammar corresponding to this largest class, so that is type 0 grammar or unrestricted grammar. So this is context sensitive grammar or type 1. So this is context free grammar or type 2, and this regular is regular grammar type 3. Now we can even make some finer classification. So if you see this thing, so here deterministic finite automata and non-deterministic finite automata are equivalent. Again here you see this deterministic Turing machine and non-deterministic Turing machines are equivalent. But in case of push-down automata, so they are not equivalent. So you have deterministic push-down automata here, and then this non-deterministic push-down automatas are strictly more powerful than deterministic PDA. And in case of linear bounded automata, we haven't mentioned deterministic and non-deterministic because in literature we do not consider deterministic LBA. So whenever we talk about LBA, it is always non-deterministic LBA. And you can define deterministic LBA and then ask whether they are equivalent or the non-deterministic version is strictly more powerful. Interestingly enough, here we do not know the answer. So whether deterministic LBA is equivalent to non-deterministic LBA or not. But by definition, whenever we say linear bounded automata or LBA, so that will mean non-deterministic linear non-deterministic LBA. Okay, so that means at least here we know that this non-deterministic push-down automata is more powerful than deterministic push-down automata. So where Chomsky hierarchy doesn't say anything about this context free part. So here there is a scope for improvement. So here we can divide it between non-deterministic and the deterministic part. So yeah, so by context tree we normally mean non-deterministic context tree, and inside that we can put this deterministic context tree. Also in this front, so you remember here we had this recursively enumerable, that means whatever is solvable by a Turing machine, and since in Turing machine this DTM is equivalent to NTM, so there we cannot make any further divide, but we can consider two different kinds of Turing machine, not in terms of determinism or non-determinism, but in terms of whether they fall into some kind of infinite loop or not. So these Turing machines are kind of general purpose computer with some program. So some programs may fall into some kind of infinite loop and may never stop. So in that sense, we can think of two different kind of Turing machines, and that will give us a finer division here. So one will be recursive and one will be recursively enumerable. So by the way, so all these are included in the bigger thing. So recursive is a special case of recursively enumerable, context sensitive is a special case of recursive, and this and so on. So here and here we can make this two finer things, and then outside this we have non-recursively enumerable. So this is the most wild thing that cannot be solved at all. So now this up to this green circle, so these are the problems that can be fully solved by a computer. Okay, so these problems, so this can be fully solved, but that does not mean that we can solve this very efficiently. In principle, they can be solved by a computer, but they might require unrealistically large time and space. So in algorithm course, you know that we always strive for this polynomial time algorithm, right? So that the problems that can be solved using in polynomial time, so using polynomial space, polynomial over the size of the input, so that sits inside this class of problems that can be solved at all. Okay, so this can be solved efficiently, and that includes all this context sensitive, context free, and deterministic context free, regular. So these are so there are efficient ways to solve all these things, whether they are deterministic or non-deterministic here. But outside this we have some problems which can be solved in principle, but which requires absurdly large amount of resource. And then outside this recursively enumerable, so these are the problems which we cannot fully solved. Okay, so what do we mean by fully solved and partially solved? So that will be defined much later in our course, after we have gone through all this regular and context free and context sensitive, this sort of thing. Okay, so but anyway, there is some notion of So in fact I can state that, see, what does a machine or automata or grammar do? So it solves a decision problem. So that means if your input string is in the desired language, in the language, then it says yes. If it is not, then it says no, right? So what I mean by this partial solution is that if the answer is yes, so then this machine is able to produce that answer yes. If the answer is no, then there is a possibility that this machine will go into an infinite loop. Okay. Now, the fallacy of going into an infinite loop is that you will not be able to tell whether you should wait more to see whether the answer is yes, or you do not know whether it's not going to stop at all, right? But here it is guaranteed that if the answer is yes, then eventually your machine will stop and say that okay, it is yes. But if the answer is no, then the machine can go into an infinite loop and you may never know what the answer is. So in that sense, the problems here are partially solved. And then you have this completely wild problems here. Okay, so here doesn't matter whether the answer is yes, no. You cannot build any computer which can even give you this partial answer that okay, if it is yes, then I will say yes, I do not know about no, or vice versa. So doesn't matter whether the answer is yes or no. You won't be able to tell either way for either possibility. Okay, by any computer given infinite space and time again. Okay, so there is no bound on resource or anything. And it's not that, see, you cannot, when I say that you cannot solve this problem using most powerful computation model, it doesn't mean that okay, it's about building another more powerful machine. Okay, we do not have it now, but maybe in 100 years we'll have a very powerful machine which will solve that thing. No, we can mathematically prove that no machine can ever solve this thing. Okay, so it's a rigorously proven non-existence result. Okay, so as I said before, Turing machines are machines which encompass the very idea of computability. If you can compute anything, that means you can compute it with a Turing machine. So these are the problems which you cannot compute with Turing machine. So that means you cannot compute it with anything else. It's not that we haven't figured it out yet. So you can prove that it cannot be done ever. So here are some typical examples of problems that we will encounter in our codes. So for example, in the very first lecture we talked about this clean star. So these stars are clean star. If you forgot the definition, then go back to the first lecture and see the definition. So you may try to prove this sort of equality. So two languages are different in different ways, and then you try to show that they are equal or not equal. Okay, so here I'm not talking about any automata or any grammar or anything. If you know the definition of language, if you know concatenation, all those things, operations on strings, then depending on those definitions you try to show that one language is equal or not equal to other, or one language include is a subset of another, something like that. Okay. And how do you prove that? Here you prove that if a string belongs to this set, then it also belongs to this set, and if it belongs to this set, then it also belongs to this set, and the usual stuff showing equality of sets, right? So then as we study different model of computations, so this sort of problems will come up, that so you remember when I demonstrated an example of DFA, and the examples were like so it was the same example which is given here. So I mentioned that it accepts a string if and only if that string represents an integer which is divisible by 3. Okay, so we tried out some examples, and that turned out to be the case for those examples, but example by proof is not proof at all. So there should be some way to prove that this model indeed accepts this language. So this sort of problems where you will encounter a model and you will try to figure out the language it accepts, or the converse problem, you will be given a language and they will be asked to construct a model. For example, here this is the collection of all strings over zeros and ones, such that this string contains equal number of zeros and ones. Now, upfront it is not clear whether this language belongs to the regular class or context free class or context sensitive class or recursively enumerable class. But if you can construct, say, a context free grammar or a push down automata, so they are equivalent, we mentioned before. So if you can construct any one of them, then you can show that this language is it actually belongs to this class of CFLs. Then we mentioned that DFAs are equivalent to NFAs, so that means given any DFA you should be able to construct a equivalent NFA, or given any NFA you should be able to construct a equivalent DFA. So here this is a NFA, so this is again the same example that we discussed before, because on 0 from this Q0 state it can either come back to this Q0 state or it can move to this Q1 state. So this is a non-deterministic behavior. So given this non-deterministic machine, so this accepts some language, it will accept some string and reject some string. So take all the strings that it accepts, so that will define a language. So now just focus on that language. Okay, so that language is what? So say this is n. So that language will be L of n. And we know, at least we have stated that there exists a DFA, right? So there exists a DFA D such that the language that you can accept with that D is the same language as this one. Okay. Now what is that D? I mean, that D may not be unique. But at least you come up with some DFAD which is equivalent with this model. Okay, so construct a equivalent model of different type. You can do the same thing with, say, PDA and grammar. So given a grammar, you can try to construct a push down automata which corresponds to the same language, right? Now this is about a specific NFA or a specific DFA. A more general thing will be to prove that for all NFA there exists an equivalent DFA, or for all CFG there exists an equivalent PDA. So these are important theorems that we will cover. So these are cornerstones of this whole topic. Uh, so yeah, we will prove this kind of theorems, which shows equivalence between different types of models. And then we will also prove that some models are strictly powerful than another. So that means what? We need to come up with a language which can be accepted by some type of model, and then we will have to show that it cannot be accepted by any model of some other class. Okay, so we will first address this sort of problem, that prove that certain language cannot be accepted by any model of a specific type, any model. So these sort of problems are harder to so this type of theorems are harder to prove, right? Because if you are asked to show that, okay, prove that this works, so then you have to come up with something and show that, okay, this thing works. But if I ask you to prove that, okay, show that this does not work for any thing, so something is not true for any prime, or something is not true for any integer, so then you cannot just give an integer or give a prime and show that, okay, this settles the thing. So you have to come up with some other clever argument to show that your statement holds for all things. So here in particular this language, okay, just this some zeros followed by some ones, where the number of zeros is equal to number of 1. So this language, we will prove later that it cannot be accepted by any DFA or any NFA, because they are equivalent, right? So we will develop something called pumping lemma for finite automata, which will enable us to prove that certain languages cannot be accepted by any DFA or any NFA. And then to prove that certain models are more powerful than other models, certain types of models are more powerful than other types of models. So we are talking about class of languages here. So if we can show that this language belongs to the class of CFLs, this context free languages, so then we would have proved that CFLs are a strict superset of regular languages, right? We also need to prove that any regular language is a CFL. So, but that part is easy, and that immediately comes from the definition of DFA and PDA. But having proved that easy part, the hard part is that to come up with some language to show that that language cannot be accepted by any DFA, and then prove that this language can be accepted by say a PDA or a grammar. Okay, so these are the sort of things we will do in our course throughout, and we will do similar things with Turing machines. But with Turing machines we have a more interesting case, because as I mentioned before, I mean, it leads to the possibility of problems which cannot be solved at all ever by any computer. Okay, so that result is a very profound and beautiful result. And another class of another type of questions that we will address is, say, suppose you have two languages, say this L1 and L2, and now you construct other languages from L1 and L2 using some mathematical operations. Say you take union of these two, or you take intersection of these two, and there are other operations between languages. I mean, you can take quotient, something will be called quotient. You can take clean closure of any of these two languages, and we will. So we also defined inversion. I mean, in the first class, we defined inversion. And we will define something called homomorphism and inverse homomorphism. So all these are ways to construct new languages from some given language or languages. So then the question is, if you know that the languages you start with belong to some language class or do not belong to some language classes, so then with that knowledge, can you prove that the resulting language that you are constructing out of these given languages using all these operations, so these newly constructed languages, whether they also belong or do not belong to certain language classes. For example, here suppose we know that this L1 and L2 are regular. So can we immediately tell from this that this L1 intersection L2 will be regular? Okay. So we will again prove several theorems like intersection of any two regular languages also regular, union of any two languages also regular, inverse of a regular language is regular. So we say that this class of regular languages is closed under intersection, union and inversion operations. Okay, so we'll prove this sort of closure properties. Also we will prove that certain classes are not closed under certain closure properties. For example, CFLs, these context-free languages, are not closed under intersection but is closed under union. So this sort of thing we will prove, and this will be very helpful in classifying problems. So you remember that in the first class itself we said that the ultimate goal of this theory of computation or complexity theory, so the next part of theory of computation is complexity theory, which is not in your curriculum. It used to be in BTech, but from this year onwards it will be discontinued. Anyway, so this is the big picture. So to classify problems in different classes, and each class belongs, each class points to a level of hardness. Okay, so if you remember, we said the goal is to classify problems according to their hardness. So the languages that belong here, they are the easiest to solve, and then these problems are slightly harder, these problems are slightly more harder, and these problems are hardest, which cannot be solved at all. These problems can be solved partially, and these problems can be solved, but again, so we said that this can be solved efficiently, this cannot be solved efficiently. So this is the final goal, okay, to to classify problems according to their hardness. And to do this, we will go through all this sort of kind of small issues, and but this closure properties are very helpful in identifying whether a certain language belongs to a class or doesn't belongs to a class. You can guess, this sort of theorems for general statements. They are very useful in putting some language in some classes.